Hey guys, we're going to talk a little bit about acceleration. Key vocab: acceleration, free fall, constant acceleration, linear graph, nonlinear graph. So let's just dive in. Acceleration is changes in speed, or changes in direction, or it could be changes in both. It's always going to be measured as a vector. Remember, a vector has change in, vector is measured in magnitude, which is your number, and a direction. So it has both. So you're not talking about the fact that it just is a number. It's going to have a directionality to it as well, which is why acceleration can also be an increase in speed or decrease in speed. So acceleration can be positive or a negative number. When we talk about acceleration, we're always talking about that change in velocity. It's not just a change in velocity, it's a change in velocity over time. One of the big ideas here is that we do have to look at the fact that there is an acceleration that happens when we talk about free fall. The idea of free fall can be seen further in a video that I added for you that's on Classroom, and then you can actually see what happens in a vacuum and how free fall works. So free fall is the change in speed simply due to the pull of the object towards Earth. This acceleration is 9.8 meters per second squared. Units for acceleration are always going to be expressed in meters per second squared. So be careful when you're looking, because this seconds squared becomes an important piece. It does need to have seconds squared, not seconds. Changes in directions might be constant, but they could just have a change in direction. That's still considered an acceleration. So an example of change in speed and direction would be roller coasters. Constant acceleration would be a steady change in that velocity. Okay, so calculating, because we all know that's the part we're really going to end up focusing on, is how to actually calculate acceleration. Acceleration is that rate at which velocity changes. So it's the rate, which means I'm working with time. So calculating straight line motion by dividing the change in velocity over time. So if you look at the equation, you have change in velocity, which is final velocity minus initial velocity, all divided by time. That equals acceleration. That's how I do the calculation. Okay, so this is giving you an example that we're looking at. This is walking you through. We'll actually do some practice ones together. So one of the big things here is to make sure when you're looking at it that you actually are reading through and finding what you need to know. So the first one is saying figuring out the information. So it's started from rest. That means the starting velocity would be 0. Time, it says after 2 seconds. That's our time. The third, it says its velocity is 6 meters per second. That would be my ending velocity. So I'm solving for acceleration. You will always write down what you know and then figure out what you are trying to figure out. Then you go to your equation and plug it in. So the acceleration is my unknown, and I have my final, which is 6 meters per second, which I got from right here. My 0 meters per second was my initial right here, and then divide by time. And when I do that, I get an answer of 3 meters per second down the ramp. Now, always look to make sure that your answer makes sense. So a free fall is 9.8 meters per second squared, and that's dropping straight down. So this is a ramp, which means it's not going to have a sharp of an angle, which means its acceleration is going to be moving at a less high of a rate, which means this one makes sense. You always have to check to make sure it's a logical answer. All right, we're going to attempt to do some practice ones here and see how it goes. Trying out the pen tool again. Okay, so very first thing I do is that I want to know what my knowns are. So my first known is, that's a starting. So I could say my VI equals 10 meters per second. It comes to a complete stop. So if it stopped, the velocity is 0. So my final velocity equals 0 meters per second. Some of you guys really like to just skip steps. And therefore, let's start again. Some of you guys really like to skip steps and not write down all the information that you know, and you really have to write down the information that you know. So this is a requirement that I'm going to make. So you have your VI equals 10 meters per second. Let's see if I can not touch the screen the right way this time. Ooh, that's a bad S, guys, sorry. And then you have your V final, which equals 0 meters per second, because we're at a complete stop. And then it tells me my time, which means T equals 20 seconds. Okay, so now I'm going to use my acceleration formula. So I have acceleration equals VF minus VI all over T. So if I plug into that equation, I'm still looking for acceleration. So A equals VF, which is 0 meters per second, minus VI, which is 10 meters per second, all over 20 seconds. So I can go through and do math on this, and I can go 0 minus 10, which gives me negative 10. So here I have, I'm going to write it next to it. A equals negative 10 meters per second all over 20 seconds. So when I'm doing the math here, meters per second divided by seconds, that's actually the same thing as meters per second times 1 over seconds. So if you have 2 seconds multiplied together, seconds times seconds is seconds squared. So in this case, my answer is going to be A equals negative 0. My cursor to do that. 0.5 meters per second squared. Okay, and this is my final answer. I would highly suggest you get the point that you are actually writing down each of our knowns and then filling in to your equation, and then at the end making sure that you're giving me a box of some kind or a circle or something to show that that is my acceleration, and make sure that you include units. All right, let's try another one. Okay, so an airplane traveling down a runway for 4 seconds. Oh, something I know, so that's my time. Time equals 4 seconds. With an acceleration of 9.0 meters per second squared. So A equals 9.0 meters per second squared. So what I don't know is the change in velocity. So I'm not looking for one velocity. I'm looking for that change. So if I go back to my equation, the parts that I know my acceleration, and I know my time. And so then I'm looking for this top part over here. So my acceleration, if I plug in, I've got my 9 meters per second squared equals, and this is going to be my unknown. I'm just going to write it as V because I know that I'm looking for the change. I'm not looking for the actual either one of the top parts. And then the bottom here is going to be 4 seconds. So to answer this, to finish this equation, I would multiply both sides by 4 seconds. Sorry. Ugh. Okay, so I just lost my problem. I would multiply both sides by 4 seconds, and when I do that, I'm just going to take off from where I was. And I'm going to say 4 seconds times, oops, 9.0 meters per second squared. So if I have seconds on the top and seconds squared on the bottom, seconds cancels and one of those s's goes away. So now my velocity, my change in velocity, is going to equal 36 meters per second. Okay, so we'll do one more. And in this case, again, we go through and we figure out what our knowns are and what our unknowns are. So we know that the pebble is going to enter at a speed of 19.6 meters per second. So that's my final. .6 meters per second. And I know I'm going to leave VI here just for a second so that we can fill that in, because we do know that. And then I'm going to talk about, I want to know how long it took. That's my question. But I do know what my acceleration is. Because it's something that's falling, that means I'm in free fall, which means my acceleration is 9.8 meters per second squared. Okay, so my initial velocity, because it's a pebble that fell, initially it's going to be sitting at 0. It's not moving when it first starts, so therefore it does not have a velocity. So if I fill that into my equation, so I have my acceleration equals VF minus VI all over my time. If I plug this in, the part that I don't know is my time. So my acceleration is 9.8 meters per second. Not too bad. Second squared equals, and in this case, our change is going to be 19.6. So 19.6 minus 0. Can we do that one right away and know that that just means that it's 19.6 meters per second? And that's divided by time. Now, this is where we've been getting stuck, is how to solve that one when it's on the bottom. So essentially what I want you to think about doing is taking and solving for t. So to solve for t, we're going to multiply both sides by t. Okay, so these two cancel. And now I would actually take and I would divide both sides by 9.8 meters per second squared. Just going to write down the numbers so you guys can see it. The units transfer with it. So we're going to divide by 9.8 meters per second. Oh, sorry. Let's try that one more time. Second squared. And when I do that, 19.6 divided by 9.8. I'm going to erase this. Okay, so I have 19.6 meters per second divided by 9 divided by 9.8 meters per second. Really bad delay on this right now, sorry guys. Okay, so my units that cancel, meters and seconds go away. But it's only one of these seconds, so therefore I'm still left with seconds. So 19.6 divided by 9.8 gives you 2 seconds. Okay? So when we look at acceleration graphs, really there's the big piece that I want you to see is the positive versus negative acceleration. So if you can see that the direction of the slope of the line, we're still talking about slope, which is going to be speed divided by time in this case. And that's going to always be what we're looking at, is speed over here and time on the bottom, so speed divided by time. Positive meaning that it's going up and to the right, and negative, and it's going to be going the opposite direction, so you can actually see the negativity. We'll work a little bit more with graphs. We'll try to do a little bit of practice with it before we actually do any testing with it. The other one that I want you to see is that when you look at acceleration over time, this is going to be a curved line. This is not going to be a linear graph. This is that non-linear graph that's part of our vocab, that as we see acceleration over time, it's going to be increasing, but it's not going to be a linear function, meaning it's going to be showing it in a curve. And that, my friends, is all of acceleration. Oh, I take that back. One last piece. We talked about instantaneous speed. We also talk about instantaneous acceleration. And this is really just looking at one specific snapshot and looking at that specific time. What is the acceleration in that specific time? Just like when we talked about instantaneous velocity or instantaneous speed, it's that one snapshot when you look at your speedometer. In this case, it's looking at a very specific time, what is the acceleration? All right, good luck, guys.